Hi everybody. Today I thought we'd have a further look at our DC Calibrator project, and we're going to have a look at improving the accuracy of the low voltage ranges, that's 1 volt and below. And to do that I'm going to add a small additional circuit and then interface that into the existing PCB. We're also going to put the project now into its project case, and I'll show you some of the issues I came across in doing that as well. We're then going to make one or two minor changes to the main PCB to accommodate some of the things we're going to do today, and we'll go through that in a little bit more detail. And then finally we'll do some testing and just look at the overall performance of the unit. So let's get started with today's upgrades. One minor change I made to the original printed circuit board was to reduce the input voltage to the 5 volt regulator. We currently have around 15 volts driving that. So I found in practice it was having to drop around 10 volts and it was running fairly warm. So I've just simply cut the track at that point there, and I've added in a 5.1 volt Zener. I'm using a 5 watt Zener, and the one I've chosen is the 1N5338, and that's just helping to keep the voltage regulator running a little bit cooler. We'll just have a quick look at how I've mounted the additional Zener on the board. You'll see that I've cut the track there between the output of the plus 15 volt supply and the input of the 5 volt regulator. Just made a small cut there on the track, and then I've just mounted the Zener across between those 2 points. So the cathode of the Zener going there, which is the plus 15 volt supply, and then the anode of the Zener going onto the input of the 5 volt regulator. Well, one of the things I'm going to try and do today is improve the resolution and then hopefully the accuracy of the output reference voltage on the low voltage settings at 1 volt and below, and I'm going to try and do that by adding an additional voltage reference source to our circuit. So let's have a look at how we're going to achieve that. Well, you see here we have a block diagram which is showing that at the moment we're using a 4.096 volt reference feeding our 12-bit DAC. And that's giving us a maximum resolution out of the DAC of 4096 of the possible steps divided into the reference voltage is giving us a 1 millivolt resolution. So that's the maximum we can get out of this per step. However, if we were to switch to a smaller voltage reference, and I've selected a 1.024 volt reference, which is a quarter of the original reference source there, that means that by dividing that total number of steps now into the new reference voltage, instead of the 1 millivolt step we get coming out, we now have 0.25 millivolt step. So we now have 4 steps for every 1 millivolt coming out of the DAC, and that's going to improve the overall resolution and hopefully then improve our accuracy at the end of the day. Now we're going to do that switching by utilising one of the analog switches that we already have on our circuit board, which is not currently being used. So I'm going to utilise that, and that's being driven by the analog pin A4 on our Arduino, which is being used as a digital output to drive that analog switch, and we're going to switch over when the voltage selected is 1 volt or less. Any voltage higher than 1 volt is going to continue to use the original 4.096 volt reference source. So let's have a look first of all at the schematic for that additional 1.024 volt reference source that I'm going to use today. Here we see the schematic for the additional voltage reference source we're using today, which is the 1.024 volt reference, and for that I'm going to use the Texas Instrument LM4140 IC, voltage reference IC. Comes in variants. I've simply chosen the one which is at 1.024 volt. Now these particular ICs are quite good in terms of their accuracy, although it's not that important in this stage. The initial accuracy is 0.1%, but the more important thing is its long-term accuracy, because we're going to trim this. So we supply this with a 5 volt input from our main PCB. So we've got plus 5 volts going in, a little bit of a decoupling there to remove any noise spikes. So I've got a 100 nanofarad capacitor there on the input pin, and we're simply connecting the enable pin of this voltage reference IC to the V-in pin, as we want it to be on all the time. Now the other important thing about this IC is it has 4 connections to ground, and it is important that all of these connections on pins 1, 4, 7 and 8 are all connected to the PCB ground. So you can see they're all joined down here. The output then comes on pin 6, that's the voltage reference out at 1.024 volts. We need to have a capacitor there, a small tantalum electrolytic 1 microfarad, to keep that voltage there stable on the output. So that's what we get at that point there. Now these particular ICs do actually come without any option of a trim pin on the IC itself, but there is a little way of getting around that. I've got this resistor network here which is giving us some form of very minor trim, plus or minus around 1 millivolt. We can trim the output of this voltage reference source. So what we've got here is a 50k 25 turn preset across the output, and then we've got this arrangement of a 1k resistor in series with a 100k resistor going to the slider of that pot, and then we're tapping off at the junction of those two resistors for our voltage reference, which is going to our main PCB. So we're going to simply trim RV1 there so we get exactly 1.024 volts. So that's a nice little technique to use to trim that voltage if you don't have means of doing it with a trim output on the IC itself. So you could use that with other voltage reference ICs in other projects. Now this particular IC is a very small SMD package, 8-pin package, and for that I'm going to actually mount it on one of these small adapter boards. This is a small 8-pin SMD to 8-pin dual inline pin converter, so we can solder the IC onto that board, and then we've got easier access to the pins at either side, and I'll show you how I've done that shortly. So there we are. There's the full schematic then for our 1.024 volt reference source for the additional circuit today. Here we have the wiring layout for this little additional circuitry. There you see the little adapter board I'm using. There's the actual board itself, and we're simply soldering the little SMD IC onto that, and then you can see here the components then wired directly onto the onto that PCB. So there you've got the 100 nanofarad capacitor on the input, and I'm showing here the links that need to be shorted out. So there's your ground points, 1, 4, 7 and 8 all joined together, and pins 2 and 3 there joined together where the input is coming in. The output there, you've got our tantalum capacitor between pin 6, the positive terminal on pin 6, and I've got that connected to pin 7, which is ground. And then we're taking the outputs then from pin 6 and from pin 8 there, and you can see here the arrangement there of the potentiometer, the trim pot, and the other two resistors, and the output there going, in our case now, going to the main printed circuit board, to the little socket that we have on that board, J2, the reference, pin 1. And we also have access on another socket on the main PCB where we can get both ground and the plus 5 volt supply. So there is the wiring arrangement, and let's just have a quick look at the board that I've put together for that. Here we can see the actual little module I've put together for this voltage reference. I've just simply used a small piece of matrix board there, just cut to size, and there you can see that the IC there on its little PCB adapter there with the two capacitors. All the links I've actually wired on that little PCB, and then the other components are on the matrix board here. So there you can see the 50k preset and the two resistors, the 1k there and the 100k there. The output then is coming from the junction of those two resistors. You can see the yellow wire coming out, and that goes to our main PCB as our voltage reference source. And the power to the module, you can see there going, the red and the black wires giving us the 5 volt supply to this little voltage reference source. So there it is. That's the little module I've put together. The power supply is going to plug onto the main board, and it's going to go to the little small connector, but I'm only using 2 pins on that, as you can see. so I'm only using one of the end pins and then the middle one for the plus 5 volt supply. And the other side, the yellow wire, that's also going to a little 3-pin plug there, which plugs onto the main board. There's 2 other wires there that also connect to the main board, and I'll show you that shortly. There's just a quick view of the underside of the board. So it's just all hand wired there, and I've put a little hole there to fix it onto the case. Now I just want to show you the minor changes we're going to make to the printed circuit on the main PCB of this project to accommodate this additional 1.024 volt reference source. And what we're going to do first of all is we're going to cut the track where the output from the 4.096 volt reference goes directly to the DAC, there on pin 13. So we're going to cut the print somewhere there, which then disconnects that 4.096 volt reference from the DAC, and instead we're going to take that voltage reference source down to this analog switch here, the spare one that we have, and I'm going to feed it onto pin 10, and you'll notice that switch and pin 10 is open by default. The other side of the switch is then going to connect to the voltage reference input of the DAC. So effectively we've put a switch in circuit there between the reference voltage and the DAC. It's currently open by default, and we can close that switch by a signal coming in on pin 9, which is from A4 of the Arduino Nano. Now our 1.024 volt reference source is then going to go to the other switch in this combination, so I'm going to take that to pin 13 there. That switch, you'll notice there, is closed by default, which means that switch on, the 1.024 volt reference source is going to be coupled directly to the voltage reference input on our DAC. So that happens at switch on, and then if we select a voltage higher than 1 volt, then the Arduino Nano is going to trigger the input there on pin 9 of our analog switch to switch that over. So that will then close, and the other switch there, which is currently feeding our 1.024 volt reference, will open. So then we'll have 4.096 volt reference going into the DAC. That's simply how we're going to achieve that today. So we're going to simply cut the print, and then having done that, we're going to then wire the signals to this analog switch here. We already have a little socket there that we're going to utilize, and I'll show you how we do that. Here we see where I've cut the track to give us the ability to switch the 4.096 volt reference. So I've just put a cut there in the track, and that's between the 12-bit DAC input, reference input, and the 4.096. So that cut there, and then we can get access to either side of that when we wire in the additional circuitry. I now have the wire soldered onto the board that's going to the 3-pin connector that's going onto the main PCB. That gives us access to the switching arrangement on the main board, and the yellow wire that goes off there goes to our 1.024 volt reference supply. Here we now have the board with the 2 connectors plugged in. The one that's feeding the 1.024 reference and the 4.096 volt reference there with the yellow, black and white leads. That wire goes under the board to the connections I made earlier. So far on this project we've had the TFT display mounted directly onto the main PCB here with some socket extensions just to raise the display safely above the Arduino Nano. And that works fine, and my intention was that once we've got the display eventually mounted in the front of a project case, that we'll simply wire it up to the main printed circuit board here using some ribbon cable like this. But when I did some testing, I found that once the ribbon cable length to the main PCB gets longer than a few inches, the touchscreen part of the display stops working. It goes a bit erratic at first and then stops working altogether. So unfortunately we can't do that, and I did look at the datasheet for the TFT display, and it did say that the length of the wires from the display are critical. So I've taken that on board, and what I'm going to do is when we unplug the display from the board, I'm going to make another small printed circuit board that mounts on the back of the display, and the Arduino Nano will then mount on that. So then the connection wires are as short as we can possibly get. And then we simply have to then take control wires then from the Arduino Nano on the new printed circuit board I'm going to make, and then wire it onto the main PCB here. So that's what I'm going to do today. Here we have the additional PCB I put together for this project. This will house the Arduino Nano and the connector that will then plug onto the back of the TFT display. It'll also have those resistors on there that are feeding the outputs from the ports to the TFT. So let me mount all the components on this and we'll come back and have a quick look. Right, well here we have the that little PCB now with all the components there populated on the board. So there you'll see the 10k resistors and the 2 wire links there, and there's the 56 ohm resistor which is feeding the LED for the display. We have 2 wire links there. You've got a long wire link going underneath the Arduino Nano, and you've got a smaller one there, the yellow one, just linking across to the 10 pin connector there. That little pin you can see there is just simply access to the 3.3 volt output voltage from the Arduino Nano, should we want to use that at a later stage. So what we'll do now is we'll simply plug in the Arduino Nano to the inline sockets there on the board, and then we'll have a look at the reverse side and see how we connect it to the display. Right, well there's the Arduino Nano mounted, so we'll just turn it around and have a look at the other side, and you'll notice now that the connection sockets there we're using are soldered on the print side because it's going to plug into the display that way, and for that I'm using some of these inline connectors that have got extra long pins on them there at the base, and that makes it easy to actually mount on the reverse side of the PCB here. These are easily available on eBay. They're actually intended for Arduino Nano extension boards, so you can get these quite cheaply on eBay. And for that I'm going to use 2 of these. One is an 8-pin one and one is a 6-pin one, so that'll give us 14 connections altogether, and we're just going to mount them butted up. What I've found in practice is that you may find the spacing is too large where they join, so we may just have to just file down a little bit on the edges where they butt up to keep the spacing consistent, and then I'm going to simply solder them on the PCB as you see here. There you see they're soldered onto the base there. There you see a close-up of how I've soldered them onto the printed circuit side of the board. Now to house our project, I've come across this nice little project box which I found on eBay. It looks very much like a sort of instrumentation box. Quite cheap. I paid £10 for this box, and it comes with a tilting bail as well at the front. So nice little box that we can put our project in. So I'll show you how we're going to do that. Right, I've just unscrewed the box. So when you take this project box apart, the nice thing about it is that the front and the back panels, they're just slotted in, so it's going to make it quite easy to mark and drill these for our front panel. So that's what we're going to do. So I'm going to take the front panel there, and I'm going to mark and drill that so we have access to our TFT display and the input connectors, and put an on-off switch on there as well. So let me look at how we're going to do that today. Now for that I've produced a front panel template here. I've just printed 3 of these on a A4 sheet. I'll make these available to you, and I'm just going to cut on plain paper. I'm just going to cut it out and use it as a template first of all, but then I'm going to print it on, you'll see here, on some glossy self-adhesive paper, so that will then peel off at the back and that will then stick on the front panel. So let me just cut off on the plain paper first as a template, and we can mount the holes. Here we have the template, the paper template, which I'm just going to overlay onto the front panel there, and all I'm going to do is simply prick through the holes that we need to drill. So you'll see the ones there, the 2 little crosses there are for the input connectors, and you'll see some small crosses there, there and there and there and there. Them 4 for the LCD, and that one there for the on-off switch. So if you can just use the template and then just mark the holes through the template onto the front panel. Here we now have the front panel, and I drill the holes, and I use a little Dremel to cut out the square for the display, and then what I've done is I've stuck the glossy front panel on the front of that, so you can see that is all now ready for the to mount the components there. And then I just cut the holes out again on the front panel with a small craft knife. All the components now for the front panel. I've got a latching push button switch there that'll fit in that location, and then for the connector sockets there I'm using 4mm shrouded sockets, as you can see here. These come in different formats, but they're all more or less exactly the same size in terms of the drill hole. I think the drill hole's around about 12 or 13 mil. And then we've also made access to bolt the TFT onto the front panel. You can see the holes there, with the connection of the TFT on this side here towards the connectors. And for that I'm going to use some M3 nylon nuts and bolts there and some spacers. So let me put all this together and we'll come back and have a look. The front panel now assembled. One important point is not to over tighten the plastic nylon screws there, as that will cause the display, TFT display, to be pressing too hard against the front panel and could affect the operation. So just sort of finger tight as long as it's secure. So there's the reverse side now of the board, and you'll notice that I've got some standoffs here on that side near the on-off switch, and that's going to support the additional PCB that'll plug onto the pins there on the display. The front panel now fully assembled with the additional PCB there mounted at the back there, just plugs onto the display, and then the pillars there just supporting the PCB. You can put some nuts on there as well. And the long connector there, the 10-way connector, is what's going to then connect to our main PCB. The smaller connectors are for future options or upgrades later. Here we have all the modules now mounted in the case, and for the on-off switch I've just simply lifted one end of the protection diode there and then wired the on-off switch in series with that to the DC input connector there. Now to connect to the main board and the display board here, I've just made up this little lead. It goes to a 10-pin plug there, and I've just put some pins on a matrix board, just glued them on with some super glue, and then just wired the connections. I'll give you the wiring details of this with the information you can download. The last thing we need to do now is just simply connect the input sockets here up to the main board there. There's the input connector socket there between the two switching ICs. So I've just got this lead then just to solder onto the input connectors and plug that in, and that finalises the assembly. Well, everything now connected up, so I think the next thing to do is just give it a quick test, make sure it's functioning. We'll just switch on and give it a test. Just check the touch screen's working, so we'll just set a voltage. That seems to be working fine. Okay. Now we no longer have the display plugged onto the main board, and all of the resistors you can see here are actually now on the small PCB behind the display. This part of the original PCB is now redundant. So what we'll be doing in further upgrades of this is to get rid of that. In fact, you could actually cut that off if you were using the existing PCB. But we're going to probably get rid of that and use this space here so we can install some rechargeable batteries. To set the reference voltage, in this case the 1.024 volt reference, I'm going to use one of the test points you can see just there. You've got two pins there. The one that's nearest to the preset potentiometer there, that's the one we're going to use. So I'm just going to plug a little flying lead in there, and then we're going to connect that to a meter. There we are, I've just plugged it in there now, so I'll zoom out and we'll have a look as we make the adjustment. Well, I have the fluke now connected to the that test point there I mentioned, and the negative end of the meter is going to the negative input on the front panel. So I'm going to switch on, and we're now going to monitor the reference voltage. It defaults to the 1.024 volt reference at switch on, so that's what we should see. Okay, so it's reading at the moment 1.025, so now I'm going to trim that preset there on the little module that we built. So let me just adjust that and see if we can get that down to 1.024. There we go. If I just take it a bit further, see how it goes to 2. Okay, so let me just set it at so you got a bit of trim either way. So 1.024. Now to just check the 4.096 volt reference, remember we set that earlier, but we have to set the voltage on the display now for a voltage higher than 1 volt. So I'm just going to do a set volts and set it to 2 volts. And what you should see is that the reference voltage will jump up to 4.096. There you go. So we haven't adjusted, well, we haven't changed it, so we've left it as it was. So the 4.096 volt reference is still at reading 4.096. If it wasn't, you could now trim the other preset, which is just there on the board. To quickly recap, to calibrate it, when you first switch on, it defaults to the lower voltage reference source of 1.024 volts. So that's what we set first. We then set the voltage on the display to a reading higher than 1 volt, and it switches over to the higher voltage reference, and then if we need to, we can adjust the 4.096 volt reference. So both the reference voltages are now set OK. So let's have a look at what the output readings are like, and we'll just for the moment monitor it on this fluke meter. We'll just go through a few voltage settings. So I'm going to first of all select 1 volt, so we monitor the input now. So let's do 1 volt, and then we'll switch it on, and we get exactly 1.000 volts on the fluke. Let's take it down to say 0.5 of a volt, and that seems to be quite accurate. Take it down to 0.25 of a volt, that's just one, well, it's hovering between one and half a digit probably out. Let's just go up now in voltage. Let's go up to say 5 volts. That's 3 digits out at the moment. Let's just check 10 volts, go to the extreme. And that's 10.00. So let's just go back. Let's have a look at 2.5 volts. That's just 2 digits out. So we could do with maybe just adjusting the calibration on voltages over 1 volt. We look as though we're probably a couple of digits out. Switch off the low. Well, I've now got the unit connected up to my Keithley 215 meter, which is pretty accurate. But with the fluke there, I'm also monitoring the reference voltage, and you can see there at the moment with 0 volt set, the reference voltage is sitting at 1.024 of a volt. So let me just select 1 volt again and see how that shows up on the Keithley meter. And we switch it on. And the Keithley is reading 1.00012 or 13 of a volt. So that is certainly accurate to 1 millivolt. I think any more accuracy than that is we're probably kidding ourselves, certainly with a 12-bit DAC. So that's very good at 1 volt. Let's go down in voltage to say half a volt again. I'll leave the output switched on. So the half volt again, that's accurate to 3 decimal places, so 0.5002 of a volt. So I'm happy with that. Let's go down to 1/4 of a volt. .25 of a volt. And again, I'm quite happy with that as well, 0.2505. So it's certainly accurate to the 3 decimal places, which is to the millivolt range, certainly in the voltages 1 volt and below. Let's just test it to its extreme. Let's go down to 0.1 of a volt. I think we're pushing it now. 0.1 of a volt. It's pretty good. 99.6 millivolts. So that is out by 0.4 of a millivolt. So I think we're pretty good. Let's go down, say, to 10. Then I think we are pushing ourselves. So let's go down to 0.01 of a volt. 0.01 volt. So it should be 10 millivolts, and it's reading 9.3 millivolts. That's not too bad. So you've noticed all the way through that the fluke on the right here is monitoring the reference voltage, which has always been 1.024. So as long as we're 1 volt and below, it's selecting that reference voltage. If I go over the 1 volt, so let me select, say, 1.1 of a volt. It'll now switch to the higher voltage reference. You can see there it's switched to the higher voltage reference at 4.096, and the Keithley is reading an output voltage of 1.104. So that looks like it's 4 digits out. Let's go up in voltage. Let's just see what the 5 volt. So we just try the 5 volt output reference, see what that's like. And 5 volts is reading 5.003. Again, it's 3 digits out on the high side, so we can probably trim that. So let's go to 10 volts. And that's 10.0018, so that's nearly 2 digits out. So we're between 2 and 3 digits out when the voltage gets higher than 1 volt. So either we can trim the 4.096 volt reference, that may be slightly out because we're only showing it to 3 decimal places there. So what I'll do in a moment, I'll just check that with the Keithley. But I would imagine we could trim that out with the 4.096 volt reference. Well, I'll now just swap the meters around. So I've got the Keithley now monitoring the reference voltage. So that's should be showing me 4.096. It's showing me 4.09595, so it's slightly low. And I've got the fluke there, which is going to be showing me the output voltage. Let me just switch the output voltage on. So let me go back to, say, 5 volts. Remember, this time the fluke is showing the output voltage. So you can see we're 3 digits out, so that was the same really as the Keithley. So what I'm going to do now is adjust the 4.096 volt reference and just see what effect it has on the output voltage. So taking the reference voltage down, we can get exactly 5 volts. Let's just select say 10 volts this time. .99. So it's actually improved things. Let's just try 2.5 volts. That's spot on again. So certainly trimming the 4.096 volt reference, you can trim out the error, and I think the error in this case is probably due to the offset error of the DAC, and we're just compensating for that by reducing the 4.096 volt reference down slightly. In this case it's 4.093. Well, just before we conclude part 2 of our project today, I wanted to have a look at the noise level at the output of this DC voltage calibrator. So I've got the oscilloscope connected to the output terminals at the rear, and we're monitoring that, and you can see there that with no voltage out, in fact the output is grounded with the switching we have on our circuit, we are getting the central bar of noise there is about 20 millivolts of noise, and then we're getting some additional spikes coming on there which are extending and giving us maybe a total of about 40 millivolts of noise. So it's still quite low noise levels, but I suspect the fact that we're getting that noise when we've got no voltage out and it should be grounded is it's pickup somewhere, or it's on the supply voltage lines. So we could actually improve things a little bit by replacing the wiring that we have coming from the main circuit board to the back of the input terminals by having that a screening wire, some shrouded wire, to help cut that down. We can probably add a capacitor across the back of the input terminal. Let me just try that, a 0.22 microfarad capacitor, and see if that reduces the noise. You see that cuts down the noise considerably. Let's just try slightly larger capacitor. I'm going to put a 1 microfarad tantalum across, and that's about the same, maybe just fractionally better. So having some capacitance across the input there just to filter out the noise, that does help. Let me now just select a voltage and see what happens to that noise level. So let's just select 1 volt. And switch it on. So we've got 1 volt there now. The noise level is about the same, so we've got a concentration of noise there of about 20 millivolts of noise. Really it's probably not that critical in this particular stage, but it'd be nice to see if we can improve that and see where it's coming from. And then the spikes, as I say, is just extending that to around 40 millivolts. So let's just increase it now to say 5 volts. And just see what the noise level is there. I've noticed there that you get some additional noise as you're keying in on the touch screen, so maybe there's some pickup there as well. Now we've actually got a little bit more noise on the spikes there at 5 volts, and that's shot up to good about 50 millivolts to about 60 millivolts of noise there in total. But again, the central noise bar there is around 20 millivolts. So I think it needs a further look at, and what we'll do in part 3 of the project, we'll have a more detailed look at the noise and just see where that might be coming from. And I suspect that the main cause of that is probably on the supply voltage rails, the 5 volts or the 15 volt rail. And we can also check what the noise level is coming out of the voltage reference ICs as well. So that's for part 3, but for the moment what I am going to do is I'm just going to put a 0.22 microfarad capacitor soldered onto the back of the input terminals for today, and just keep the noise level as low as possible. Right, well I've now just soldered that 0.22 microfarad capacitor at the rear of the input terminals there, and that's certainly cut down the noise now. So the main noise concentration there is now down to around 10 millivolts, and the spikes that we can see just extend it down to around about 30 millivolts or so peak to peak. So we managed to cut it right down, but in part 3 we'll have a closer look at the noise. I mean, at this level it's not critical, I think it's quite acceptable, but we will have a look and see where that's coming from in part 3 and see whether we can do anything to improve it further. So I'm going to leave it there for today. Just before I do that though, let me just switch the voltage level on the scope so you can see it now. So I've got the scope set to 10 millivolts per square now on the oscilloscope, so you can see that the main band of noise is filling one segment there, one square of the on this, which is 10 millivolts peak to peak, and then you've got some additional spikes top going from that. So that gives you an indication of what the noise level is like on this at the moment. Anyway, so let's leave it there for the moment. I'm still quite happy about that. As you can see, the voltage reference output is looking quite good, and the noise level I think is acceptable at this stage. Well, I think I'm going to leave the project there for today. I hope you've enjoyed the progress that we're making on this. What I will be doing in part 3 of the project is having a more detailed look at calibration, and maybe have a look at even further upgrades that we can consider for this unit. I'll also look at maybe redesigning the PCB for a double-sided print, which will make the main PCB much smaller, and I'll see about having those made professionally. If that proves successful, then I may be able to make some of the boards available to you for those that are interested. In the meantime, what I will do is I'll put some links down below, and you can download the latest updates for the project, and I'll also put there the latest version of the software which you will need if you're going to use the upgrade for the additional voltage reference. So thanks for watching. If you found this useful, please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.